Everybody look left. Everybody look right. Everywhere you look, I'm standing in the spotlight.
Hi, everyone. In the last video, we introduced the second version of the fundamental theorem of calculus. It said, suppose that little f is a continuous function on the interval from a to b, and capital F is any antiderivative of little f. Then the definite integral of little f from a to b is just equal to capital F of b minus capital F of a. And we introduced this notation, capital F of x, with this bracket and b and a, because that'll make it a little easier for us to write. So in this video, I just want to do a lot of examples. So first, let's take the integral from 3 to 7 of 2x dx. What is that? Well, FTC2, what do we need? We just need to know some antiderivative of the function 2x. What's a function whose derivative is 2x? Well, 1 is x squared. So I have this function x squared, 7, 3. This means x squared evaluated at the top endpoint minus x squared evaluated at the bottom. So this is 7 squared minus 3 squared, which is 49 minus 9, which is 40. OK, exercise. You really should try it. Show this with the limit definition, where you take the limit as n goes to infinity of this approximation with rectangle areas, either Rn or Ln. This is much easier. FTC2 saves you a ton of work. OK, next example, the integral from 1 to 4 of 3 times the square root of x dx. Well, I find it a little easier to rewrite this a little. This is 3 times x to the 1/2 dx. So what is a function whose derivative is 3 times x to the 1/2? Well, by the power rule, if you take a derivative of some number times x to the 3/2, the exponent comes down by 1, and you'll get some number times x to the 1/2. So the question is, what is that number? So it's going to be something times x to the 3/2 is our antiderivative. If you take the derivative here, you get 3 over 2. And we want the 3, but we don't want the over 2. So you can check that 2 x to the 3/2 is an antiderivative of 3 times the square root of x. You take the derivative, you get 3/2 times 2, which is 3, times x to the 1/2. Evaluated at 4, evaluated at 1. So what is this? This is 2 times 4 to the 3/2 power minus 2 times 1 to the 3/2 power. What does it mean to take something to the 3/2 power? Well, you can take it to the 1/2 power and then take the cube. So this is 2 times square root of 4 cubed minus 2 times 1 to any power is just 1, so minus 2. And square root of 4, let me put parentheses here. Square root of 4 is just 2. 2 cubed is 8. This is 16 minus 2, which is 14. Again, you could do this using this approximation using rectangle areas, but it's a lot more work. OK, let's do the next one. So a different kind of example, one that comes from trig. Let's do the integral from 0 to pi of, let's say, 5 times sine theta d theta. Well, this is going to be, what's an antiderivative of 5 sine theta? An antiderivative of 1 sine theta is negative cosine theta. So one antiderivative of 5 sine theta is negative 5 cosine theta, evaluated at 0 and pi. So we get negative 5 cosine pi minus, and we have to be careful with parentheses, negative 5 cosine, negative 5 cosine of 0. This is negative 5 times negative 1. So this is 5 minus 5 plus cosine 0. 5 plus 5, which is 10. Okay, so the tricky thing here is just being careful with the parentheses because we have a negative in our antiderivative. Okay, let's do the integral from x to 7x of 1 over t dt. All right, so this one is a little different because we don't have numbers in here now. We have x, 7x. But if you put in any number for x, this is going to give you the integral from a to b, like 2 different places. So like if x is 1, you get 1 to 7. If x is a half, you get 1/2 to 7 halves, and so on. If we want to apply FTC2, we need little f, 1 over t, to be continuous on the interval from a to b. And 1 over t is not continuous everywhere, but 1 over t is continuous on the interval from x to 7x for any x. Why is that true? Because x and 7x are either both positive or both negative. In the case when they're both 0, then you're just getting the integral from 0 to 0 is just 0. So let's say x is not 0 because that function's not defined here. But if x is positive, 1 over t is continuous on x to 7x. If x is negative, 1 over t is continuous on x to 7x. So that means we can just evaluate. So what do we get? What's an antiderivative of 1 over t? Well, it's natural log of absolute value of t, evaluated at 7x and x. And let me move up to the top here, because I want to have some extra space. So what does that give us? So what we get is this is equal to the natural log of the absolute value of 7x minus the natural log of the absolute value of x. And we could stop there. This is a correct value for any x not equal to 0. But we can actually say a little more. Remember, there are some properties of logarithms that will be useful to remember throughout this course, that the natural log of a over b is equal to the natural log of a minus the natural log of b. This property goes along with the natural log of a times b equals natural log of a plus the natural log of b. So what does this mean? That this difference of logarithms is equal to the natural log of the absolute value of 7x over the absolute value of x. So what does that mean? Well, the absolute value of 7x divided by the absolute value of x is just equal to 7. For any value of x that's not 0, this is just equal to the natural log of 7. What does that mean? We started with an integral that went from x to 7x. And the answer we get does not depend on x. I think that's pretty cool. So this doesn't depend on x. And if you don't believe me, just try it. So try the integral from 1 to 7 of 1 over t dt. Or you could try the integral from 100 to 700 of 1 over t dt. or the integral from -2 to -14 of 1 over t dt. And you'll see that in all of these cases, which are all instances of this integral for different values of x, you're going to get natural log of 7. Okay, let's just keep going. Let's do some more examples. So I want to give you one that comes from a different kind of function. Let's do the integral from 0 to 10 of e to the minus t dt. So this function is continuous. There's no problem at like t equals 0 or anything like that. How do you find an antiderivative of e to the minus t? We know an antiderivative of e to the t. So what happens when you take the derivative of e to the something? You get some constant times e to the something. So let me just say we know d dx of e to the minus x is equal to e to the minus x. But then by the chain rule, we need another factor of the derivative of the function of x in the exponent. So times -1. So that means minus e to the minus t is an antiderivative for e to the minus t. So this is equal to minus e minus t 0, 10, which is minus e to the minus 10 minus e to the minus 0. What is that? Minus minus, we get a plus. E to the minus 0 is e to the 0, which is 1. This is just 1 minus e to the negative t. So let me say, one of the things that people struggle with most in Math 2B isn't actually this new calculus type material, but just getting comfortable with this kind of algebra again. Okay, let me do another example. In this integral of 1 over t from x to 7x, we had not a number in the bottom and top endpoints of our interval, but a function of x. So you could have the same thing where you just have a variable in one of these endpoints rather than both. So something like the integral from h to 1 of 1 over the square root of x dx. So again, these things with square roots, I find it a lot easier to just rewrite these functions as x to the something. How do you find an antiderivative of x to the minus 1/2? Well, the derivative of x to the half is some number times x to the minus 1/2. So we just need to figure out what constant we want in front of our x to the 1/2 so that the derivative is x to the negative 1/2. And it's not difficult to see that this should be 2x to the 1/2 evaluated at h and 1. So we get 2 times 1 to the 1/2 minus 2 times h to the 1/2, which is just 2 times 1, 2 minus 2 times the square root of h. Okay, we have to be a little careful here because we need our function 1 over square root of x to be continuous on the interval from h to 1. So the problem is that 1 over square root of x is not continuous at x equals 0. It's not even really defined when x is negative, because a square root of a negative number is some imaginary complex number. So this is true for any h greater than 0. Okay, so when applying FTC2, you should at least take a second and think about where your function is continuous and defined. Okay, let me just keep going. Let me do a couple more examples. There's nothing tricky going on. I just want to show you all the integrals that we can compute now. Like integral from minus pi over 3 to pi over 3 of 2 minus secant squared x dx. Well, first thing to do is this is the integral of a difference of two things. It is the difference of the integrals. So the integral from minus pi over 3 to pi over 3 of 2 dx minus the integral from minus pi over 3 to pi over 3 of secant squared x dx. I know the integral of a constant function. It's just c times b minus a. But you can also do it with FTC2 and say an antiderivative of 2 dx is the function 2x evaluated at the top endpoint minus the evaluation at the lower endpoint. An antiderivative of secant squared, that's one of the ones we know. We can take tangent of x evaluated at the lower endpoint, sorry, at the top endpoint minus the evaluation at the lower endpoint. So what we get here is 2 pi over 3 minus 2 negative pi over 3 minus tangent pi over 3 minus, let me be a little careful here. Let me put a parentheses. Tangent pi over 3 minus tangent of negative pi over 3. OK, let's just unwind all of this. So the tricky part here is just being careful about the algebra. So 2 pi over 3 minus minus, this will turn into a plus. What we get is 4 pi over 3. What is tangent of pi over 3? Well, what values of sine and cosine do you know? Starting from 0, we have pi over 6, that's 30 degrees. Pi over 4, 45 degrees. Pi over 3 is 60 degrees. So that's where cosine is equal to a half, and sine is equal to square root of 3 over 2. So we get minus sine over cosine, so square root of 3 over 2 divided by 1/2. That's just square root of 3. And here we have a minus minus plus tangent negative pi over 3. The only difference is now sine is negative, so minus the same thing, square root of 3 over 2 divided by 1/2. So in the end, this is 4 pi over 3 minus, this is square root of 3. And this is negative square root of 3. So we get minus 2 root 3. OK, so this is just to give you a feeling for all of the different integrals that we can now compute using the second version of the fundamental theorem of calculus.